you get
there aren't too many armies. You know, you gotta be.
When you get a solid dissolving in water, sometimes you can get a release in heat energy or a change in heat energy. And this is because there can be a more favorable stabilization of the ions or the molecules once they're dissolved in the water. So let's go back and talk about this a little bit. So if you think about the interactions between sodium and chlorine that are occurring here, they're stabilizing each other. They have charges. They need to kind of lend electron density to each other, right? And so they're stabilizing each other. And their proximity is allowing that to occur. Same with, let's go this way. Same with this structure, which represents sugar, right? A compound, sugar cube or something like that, right? Just a solid of sugar. The two or multiple molecules of sucrose that come together, when they come together, there is a degree of stabilization, just like any two molecules. If they can come together and stabilize each other, then they become sticky, harder to separate. If water comes along and does separate them, that separation is usually going to occur because they're more stable with the water. And if they're more stable with the water, then there will be a change in heat when that stabilization occurs, or that solution, solvation occurs. So in other words, you take a salt, you put it into water, mix it around, and the salt might get warm, right? Warm. Energy is released because the water can stabilize those ions better than the ions could stabilize themselves when they were in the solid form. And we're familiar with this in the form of heat packs. And in sports, you have these packs that they're room temperature, just sitting around, and then you crinkle them up, move them, and what that does is it allows a solute, like a salt of some kind, to interact with water, and the result is a release in heat energy because there's a change in the amount of stabilization that occurs, and this is called a delta H of solution. This video here talks about...
There aren't too many armies. You know, you gotta be a pretty developed country before you're gonna be able to pull off packaging food for prolonged periods of time.
All right.
Hi, I'm Stevie Hansen with Meal Kits by Canada.
We have what are called meals ready to eat for the United States Army and for a lot of the westernized world. And it's really interesting to me, the way that these meals ready to eat, and I have some here. I'm always tempted to eat them, but it's basically a bag of stuff. And inside, let's open one up. Why not? Write yes in the chat there if you're familiar with these MREs. Okay, Robert, were you in the military or had family in the military, or how did you become familiar with them?
I've had a few friends, and they just are not the best. But yeah, I'm familiar with. Yeah.
So you don't like MREs?
The majority, no, but I mean, some of them are not half bad.
So here's what we got. We get some French vanilla cappuccino instant powder. Crackers. Those are going to be, the crackers, that's cold. The French vanilla coffee, I think they're planning on us eating hot, right? Crunchy peanut butter, that's going to be cold. All right. Dry roasted peanuts. Wow, that's good. Cran raspberry. Yes, energy bar. Okay. Now I'm showing you all this, taking the time to show you all this. This one here doesn't have a big label, but it's mixed fruit. And this is my main dish here, vegetarian taco pasta. vegetarian taco pasta. Now, depending on how free you want your country to be, you have to decide how good of a meal your soldiers are going to eat, especially if they're up at the front lines protecting us somehow, right? And there's a pretty good relationship. You can look online and look at the countries, how they feed their armies. And if they're feeding them cold food, the armies don't last very long, all right? The morale goes down fast. People are used to eating warm food and they want to do that, okay? So how do I get warm food? How do I get warm food? Well, what I do is I take advantage of my delta H of solution. The fact that you can mix some chemicals with water and it will warm up that water, okay? And that's this little container right here, right? If I snip off the top here, in this little package here, I have some salt, some little salts. Now this package right here is not going to be where I put I think I need to save this here. This package here is not going to be where I put my food. Let's see. What I'm going to do is I'm going to slide this in there like that. This is going to be my heater. And then I take my Taco Surprise and I put it in there, flip open this top, pour in a little bit of water. So I do need a little bit of water. And then I just kind of let it set there for a while. This will get really hot and it will warm up my Taco Surprise. And then I can open it up. I should probably open it up just a little. Well, I guess I don't think it matters too much. But if I open it up and then stir it to kind of get the heat distributed, this will be nice and warm. And I can do the same thing. I can also put in my coffee as well, right? So I can have both of these in here and warm them up. All right. So this delta H of solution occurs when you mix a solid into water. The solid dissolves in the water, and because the solid prefers or has found better intermolecular interactions with the water than it did with itself, then heat is released, energy is released. Okay, so let's see. Are they like Mountain House? What's Mountain House? MREs just aren't dehydrated. Is Mountain House where it's landing? You want to tell us about Mountain House?
Yeah, mountain houses they're like kind of like that, like packaged foods, and you just add hot water to them, and then you can have like spaghetti or chicken Alfredo, or you can also have desserts like the cranberry. So I was just wondering what was the difference between those and then these MREs.
What'd you decide? Did you figure it out?
I mean, Robert said that they aren't dehydrated because, yeah, I think so. I think I got it.
Yeah. Can you, if you take Mountain House and just put regular water, will the food be warm?
No.
Yeah, no. Oh, here's the pouch. Here's the pouch. You can have
the biggest thing is just like the Mountain House and then the backpacking, like they're designed like that just to reduce the weight, like just to like strictly reduce the weight. Whereas like the MREs, like it's not as big of a priority, I guess.
Yeah, they're just trying to make sure that people have kind of high calorie and hopefully warm meal. Okay, very good. So, delta H of solution occurs, or there's a change in the heat of solution, when you mix a solid and a liquid together. And you can think of it this way. Here's my solid, here's my water. That's the energy of both of them. To mix the solid with the water, I need to separate all of these solid molecules, whatever they are, atoms, whatever they are, ions, from each other. And to separate them out, it means I need to remove all of their intermolecular forces to pull them all apart. And that requires energy. But when I put them in with the water, then the new intermolecular forces will stabilize the intermolecular forces that we're trying to overcome and bring the energy back down again. Sometimes, even though the resulting energy change here, so for example, for this one, you have an energy change where it's a positive kilojoules per mole. Positive, meaning this isn't an exothermic process, it's an endothermic process. And the resulting the resulting mixture, will feel cold to your touch. And they have cold packs like that as well if you need to cool down a certain area on your body. It depends on how much of this release you get compared to how much is required to separate them. But you could get a negative delta H, or you could get a positive delta H. Now we'll talk more about that negative delta H, because you might say, well, wait a second. If separating requires a certain amount of energy and coming back together again doesn't release as much, well, then why would they do it in the first place? Okay. And sometimes there's another driving force, which is called entropy. And we'll talk about that in the future, but that's important to know. All right. So the same thing can occur when we take liquids and combine them together. And we can think about that occurring in a couple of steps. One, an endothermic process where to separate these liquids, right? Some energy has to go into the process. And then when they're allowed to mix together again, that would be our exothermic, our energy releasing step. So you can have this delta H of solution occurring for solids with liquids, or even two liquids, mixing them together. And in the end, the new liquid might be warm or it might be cold, right? It's because the intermolecular forces that are now interacting with each other are different than they were individually. Okay? Let's see. Same thing can occur with gases. Here's gases. To allow the gas to go into the solvent, you need to expand the solvent. So you're kind of overcoming the intermolecular forces associated with the liquid to allow the gas to interact there. And the result might be, again, an endothermic delta H, or it could be an exothermic delta H. Okay, so we talked about the saturated solutions being in an equilibrium, where you have a solid here, and the solid is dissolving into the solution. At the same time, the dissolved molecules or atoms can also come back to the solid. And so there's a constant change of the molecules that are in solution compared to the ones that are still in the solid phase. All right, saturation. Supersaturation, that's also a scenario that you can get. So if you heat this up, more of your solid will dissolve in the liquid. And then as you slowly cool it down, the dissolved material will have a little bit of a harder time finding each other. And so you have, for just a temporary amount of time, what's called a supersaturated solution. That brings up this fact here that solubility varies with temperature. And that's something I think we already know, because we've been familiar with a couple things. One, if you take sugar, and I'll ask who's up, Landon. Have you ever put sugar in your cereal, Landon?
No, but
No.
I think I know what happens if, like, you get down to the bottom and then you have all the leftover sugar
I
at the
think the
bottom.
more important question is, why haven't you ever put sugar in your cereal?
I don't know. I've always liked the taste of just. I mean, I've put fruit in my cereal, but
Okay.
I've never had to add sugar.
What kind of, so maybe it's a generational thing. Maybe this is no longer a question. Maybe, I don't know. But used to be that sugar or cereal tastes like corn, or not cornflakes, sawdust, right? And
Okay.
it was okay, yeah, whatever. But I mean, you had to have some flavor in it, so you put some sugar in it, especially for the kids who were kind of wanting something sweet. But
Uh-huh.
yes, what happens when you put the sugar into the cold milk, Landon?
It doesn't dissolve.
Yeah, some will dissolve, and that's
Oh
what you
yeah.
taste. But when you're done, you have a little mound of sugar at the bottom.
Mhm.
And that's not because sugar won't dissolve in milk. It's because sugar has a hard time dissolving in cold milk. Cold milk. So that's another example of how solubility will vary with temperature. So hopefully that example will help us recognize that if we want to dissolve something more in a liquid, we have to raise the temperature of the liquid. Okay. Hopefully we also have that experience with salt in water. If you put a lot of salt in water, the salt eventually will make a mound on the bottom. But if the water is heated up, the salt will also dissolve. It's a very important principle for making solutions that are higher concentration than, some compounds won't necessarily exceed their threshold of solubility, but you need to have some heat to kind of convince them to dissolve in the first place. All right, so what we need to remember there is the trend of solubility with temperature. Solubility of, I should say, solid into liquid, because it's different for gas in a liquid. It's different for gas in a liquid. Let's talk about that. During the Industrial Revolution, factories were built on rivers, and the rivers would use the factories would use the rivers as a source of water to cool the machinery. And they still do this. And the hot water was dumped back into the oceans. And fishes began to die, and people would say, well, wait a second. Those factories are polluting the rivers. And so they would look for signs of pollution, but they couldn't find any. They couldn't find any clear indication of toxins or oils or anything like that were being released from the factory into the rivers. But anybody have an idea? Anybody want to say yes in the chat box if you know why the fish were dying? What do you think, Robert? What's going on here?
So I had worked in a refinery, and we kind of used the same process. They sucked water out of a river just to cool all the equipment throughout it. And my presumption is the change in water temperature and how it affects the ecosystem. So when they jet all that back in, I mean, it's completely, it can be, a 20-degree difference or a 10-degree difference, however much it is. And it would just kind of destroy that section of the river. And so if nothing can really flow up or down the river, it kind of affects the whole ecosystem.
Okay, very good. And the reason why is specifically, as you increase temperature of a liquid, then the amount of oxygen, or any gas for that matter, that can dissolve in it decreases. Now, this is opposite than what we just talked about, right? We just talked about how solids can dissolve in liquid. And to increase the amount of solids that dissolve in liquid, one thing you can do is to warm the liquid, right? However, for gases, if you want to increase the amount of a gas that can dissolve in a liquid, you need to lower the temperature of the liquid. And this is, we have some experience with this with soda pops. You get a can of soda. If you leave it out in the heat for a long time, then you open it. When you open it, a lot of the carbon dioxide will be released, right? If you leave it out in the heat for a long time, but then put it in the fridge, you won't lose the carbon dioxide because the carbon dioxide will redissolve into the water, which is the soda, right? As it cools down, okay? So that's one way that we can remember the relationship. there's two things, right? Solid dissolving into liquid, that's our sugar in our cereal milk. And then the gas dissolving into a liquid, that's our soda pop. Gas will come out at higher temperatures, right? We also know that if you shake it, it'll come out. If you heat it up, it'll also come out. Okay, so that's a good place to stop. Next time we'll talk about how we can actually do some math to determine how much gas can specifically dissolve into a given solvent.